Good afternoon for those in Europe and good morning for those in the United States. We are on the second day of our conference on the economics of climate change. This session, we will have two speakers, Eugenie Dugoua and Tony Smith. And we will start with Eugenie, who will talk on induced innovation and international environmental agreements, evidence from the ozone regime.
First, I'd like to thank the organizers for including my paper and for putting together this great workshop. It's been really a pleasure yesterday to listen to all this fantastic research ideas and results. So broadly speaking, what I'm going to talk about today is the idea of induced innovation, or sometimes also called directed technological change, in the context of international environmental agreements. And I'll specifically focus on the case of the ozone regime. Global collective action problems are arguably some of the most pressing issues that humanity is facing. And unfortunately, progress has been quite limited, in particular with climate change or biodiversity. There is, however, one shiny exception, which is the fight against ozone depletion. And this may seem like a long forgotten issue, but in fact, in the 1980s, this was the #1 environmental problem on the global stage. So ozone depletion is caused by industrial gases called CFCs. In '87, an international agreement was successfully negotiated, the Montreal Protocol, and stratospheric ozone has been under recovery since then. I think this really presents us with a formidable opportunity to understand what worked in that case. And in this paper, I focus on the role of science and innovation. In particular, I ask whether the agreement induced innovation. There are no quantitative analysis on this topic up to now. I think understanding how we can induce green innovation in the context of global collective action is really critical, because often better technology is really our best bet for, in practice, reducing emissions. So in this paper, again, I asked whether Montreal fostered science and innovation on CFC substitute. I use data on patents and scientific articles, and I tracked through these documents which documents are mentioning CFC substitute. Doing this, I construct panel data sets of the number of documents over time that mention particular molecules. I use a difference in difference and a synthetic control method to try to identify the causal effect. And I use as control units there a group of molecules called hazardous air pollutants. I also leverage recent advances in computer science, mainly on text analysis, to model the topics present in these documents. That helps me construct molecule level topic proportions, which will help me account for possible confounding. And finally, to discuss my results, I go back to the theory on international environmental agreement. I sort of do a slight modification of the workhorse model in that literature by adding induced innovation, and show how my results can be interpreted in this context. So as a preview of what the raw time series looks like of the number of articles and patents over time mentioning CFC substitute, here is what the trends look like before '87, before Montreal. There's almost little signal, little activity there, very flat, and then a huge burst after '87. When I run the analysis using a control group, I find similarly strong significant effect. The result with the SEM are slightly more conservative, but still around more than 100% increase. And now I also investigate an alternative hypothesis that this idea that CFC substitutes were already there and they had been kept secret and so on. That is a widely adopted narrative. People argue that's kind of why the industry would have endorsed CFC cuts, because supposedly they had achieved a breakthrough. And I want to say upfront that this narrative seems to really not fit well with the nature of the technological challenge here. It's important to understand that in this context, the challenge is not about finding new molecules. These molecules, the substitutes, they've been there for a long time. It's more about experimenting with a lot of many different molecules on several industrial applications. In any case, the approach I take here is, kind of step aside from a lot of the speculation that has been going on this narrative, and I want to see whether the data can talk. In particular, I try to falsify this claim, and I argued that if any secret technologies existed, then firms would hurry and get patent protection. And therefore, if this secret substitute existed, I would see some sort of immediate peak patenting, which is not what I observed. People have often wondered why firms would be in favor of a treaty if it was not because they had this secret substitute. Well, in fact, in this context, as long as firms can pass down costs to consumers, for them, what matters is that they are in a level playing fields. So as long as their international competitors are faced with the same constraint, in fact, they have no particular reason to oppose. Okay. So in another way of saying this is from the firm's point of view, this is more of a coordination problem than really a prisoner's dilemma. So in the next few minutes, I will tell you a bit more about the empirical work that I've been doing, and then I'll discuss how it connects to the theory on international agreement. So this paper is broadly relevant to two strands of the literature. The first is the economics literature on induced innovation and directed technological change. There is not much there on international agreements. It is also, of course, relevant to the very broad, vast literature on the Montreal Protocol and the ozone crisis. Many people have compared this crisis to climate change from various perspectives. There are no empirical quantitative analysis of innovation and science in this context. And I think that might explain why opinions on the role of innovations are pretty mixed. So I've put up here two different quotes, maybe at the two different extremes of opinions here. The first is from the head negotiator at Montreal for the United States. In his view, it's evident that the protocol is doing something. It is changing what firms are doing, even compared to just 2 years earlier. But then you also find, and here is a quote from the New York Times, often again this narrative that the solutions were already available. There are no debates, however, on what happened next, meaning the consumption of CFCs really dropped. CFCs were used in many different industries. And although the overall market was small, it's important to keep in mind these molecules were a little bit like the wonder, the miracle of modern chemistry at the time when they got developed and discovered. And they ended up being used in so many different applications. Every car around the world had an AC unit in them. All the cars that had an AC unit, their AC units was made complementary to CFCs. Electronics also were cleaned and manufactured using CFCs. So the amount of goods, services, and capital that were complementary to CFC was much larger in value than the market for the said molecules. The story of the ozone layer begins in the middle of the 70s. There was an early mobilization, but that early mobilization quickly collapsed at the beginning of the 80s when you had very strong anti-regulatory administration elected, particularly in the US with Reagan and in the UK with Thatcher. Towards the end of the 70s, because of a little bit of public pressure, some firms announced that they would start working on R&D for substitutes. And then when this new administration got elected, soon they announced, well, actually, we're shutting down these R&D programs because there are no sign of upcoming regulations. But meanwhile, diplomats were still very active and hopeful and continued to set up an international infrastructure to discuss this issue. And eventually in '87, Montreal would be successfully negotiated and ratified by the different parties. What Montreal did was agreeing on particular targets of reduction. And you could think of this target maybe as not so ambitious. For CFC 11, for example, you had the freeze by 1989 and only a 50% cut by 98. You know, what you could think of something ambitious here would have been a full ban. This was only agreed later on in London and Copenhagen, which were two amendments to the protocol. So even though Montreal was maybe not so ambitious, it was binding. And what I mean by binding here is economically binding. The enforcement mechanism was running through trade restriction that was imposed on non-parties in products containing CFCs. And there was also the threat of banning trade in products made using CFCs. As two side notes here, the first thing that I want to highlight is that domestic regulations kicked in at some point, but that is only later on in the time series. In the US, that's in 1994, so about 7 years later. And also I want to add that Montreal is not without some element of political surprise. As I mentioned before, the context in the US and in the UK was very anti-regulatory. But on the European side, it really helped that the UK left this European Committee presidency, which was tasked with leading the negotiations. So as soon as the UK left, the only head negotiators were countries that were not major CFC producers and that also wanted to make progress on ozone protection. Also, people highlight that Reagan overruled his own administration, and that came really as a surprise. He approved the agreement despite having been anti-regulation for a long time. And some people have suggested that the fact that he had actually skin cancer removed twice may have weighted on his conscience quite a bit. So in terms of the data that I use, let me just make a point about, again, the nature of the technological challenge here. I put up there different molecules. On the left, you have this one CFC molecule. So this is the bad guy that needs to be phased out. And on the right, you have 3 examples of possible substitutes. And what should strike you about these molecules is they all look kind of the same. In fact, the reason why CFC were so attractive from a point of view of industrial applications is because their thermodynamic properties are quite amazing and they're non-toxic. So if you want to substitute this bad guys, you need something that approximates the thermodynamic properties. And these properties are determined by the molecular structure. So chemists knew very well the range of molecules that they had to consider. So in a way, I just again want to highlight here that the problem was not new to the world molecules. The molecules had been in the public domain for a long time, but it was a new to the industry type of problem. The problem was about experimenting to figure out how to make large-scale production cost efficient, how to redesign processes, equipment, and also learning about environmental acceptability and human toxicity. And so in my empirical strategy, I compile a list of 14 molecules that are identified as potential substitutes. Then I track these molecules in the corpus of patents and the corpus of scientific articles. Patents here are great to capture any new work innovation on process or formula designs, whereas scientific articles will help me capture work that cannot be patented, but that is nonetheless really important to do to ensure a smooth transition, like understanding the thermal properties, the toxicity profile, and how bad this substitute may be reacting in the stratosphere with ozone. So for my empirical strategy, here I use a control group, which I argue is appropriate because these molecules are also used in the chemical industry, and they're they're related to very similar industrial activities. And importantly, they have no connection to ozone depletion. There is some potential concern that there's some regulation kicking in the later part of my time series, so I truncate the time series to avoid any interferences. So I truncate to 1992 and 1995 for articles. Now, regarding how I use topic modeling, I use topic modeling to ensure that the control molecules that I use are similar. The basic idea here is to look at the words that are mentioned in documents about a particular molecule. And that will capture what this document is about, and therefore what the molecules are about. The chemical characteristics, but also the, more generally speaking, the industrial characteristics. So I use an algorithm here that I've been used many times before, including in social sciences. This is latent Dirichlet allocation. To give you an example of the topics that I get here, here are some on the left or some example for patents, and on the right, some example for articles. You see, these are very technical words, obviously, since the two corpora are very technical. But then the algorithm can tell me for any particular patent, what are the proportions of these different topics in that particular patent. Then I aggregate this at the molecule level. So that allows me to construct variables at the molecule year level that helps me control for industrial characteristics in the definitive. And in the SEM procedure, I use this as matching covariance. So here are the pretrends that I get for the difference in difference setup. Here again, the HAPS molecules actually are a large group of 200 molecules. So I focus here on the HAPS that are going to be most similar to CFC substitute. The pretrend are very comparable, both in the patents and in the case of articles. The difference in difference coefficient plots here show the regression specification without controlling for topics. Now, when controlling for topics, it actually makes the treatment effect a little higher and more significant. We see that the treatment seems, the effect seems to pick up in year 2 after 87 for patents. The signal is slightly more noisy for article. But actually we see a takeoff with a significant effect in year 1 already. So I run a series of robustness checks, which I'm happy to talk about. I also run an alternative or implement an alternative empirical strategy using synthetic control. And the reason I do this is that if you think about all the molecules I'm looking at here, here are 14 different substitutes that I study. So they're all here, and you can see their different signals. And the diff and diff consider them as independent. But in reality, these signals are not really independent because patents and articles often mention these molecules in the same documents. So to circumvent this issue, you could also consider that all these molecules could be together. Like here's the signal for all these molecules aggregated together. And so instead of trying to estimate the effect on the average molecule, which is what the diff and diff does, you could think of trying to estimate the causal effect on this subfield of science and technology, which is work on CFC substitutes. The synthetic control method will help me construct a synthetic control for this black line here, for this aggregate CFC substitute. And I'm gonna fly through results here. I also have a bunch of robustness check, but the graphs look like that, a very large treatment effect. I implement also the placebo test that are typically used in the SEM type procedures to test whether the signal, the treatment that is measured is significant. And I also find that this treatment are significant by this non-parametric test. All right, so in the time that remains, I want to spend a bit of some time trying to look into this alternative hypothesis of secret substitutes, and then discuss how my results connect back to the theory. So as I mentioned before, there is this widely heard hypothesis that maybe the substitutes were already there, possibly because the R&D was done before and firms kept substitute hidden. There's a lot of speculations. You can find arguments in many books and articles in favor of that and or against, and it's really not clear where the statements come from. So here I'm just trying to take a data-driven, an empirical approach, trying to see whether the data can help us falsify any of these claims. And I argue that patent data can help us falsify this claim if we can make the assumption that trade secrets are not a powerful mechanism at play here. If you think trade secrets are powerful, then whatever you observed in patenting may just be a fraction of the reality of the real innovation effort that's being undertaken. But if there are no trade secrets, if most of the inventions, if the only way that firms try to get protection for their invention is through intellectual property rights and patenting, then we can falsify this claim about hidden substitutes. And here I'm going to argue that we have good evidence, there are good arguments to make that it was hard to keep these things secret. The trade secret mechanism is unlikely to have been effective here. The first argument for that is if you think about the remaining barriers to developing substitutes. The first one was about proving suitability for specific applications. And this is impossible to do just internally. You have to partner with your customer to do that. So if you want to figure out a way of substituting CFCs in air conditioning units that goes into cars, you're going to have to, in fact, collaborate with these car manufacturers, suppliers. So that is really difficult to do in secret. The other aspect was about developing synthesis processes. This could potentially be done in secret, but here I want to make the case that there are many competitors. The chemical industry is a very competitive industry, and they're all working on the same molecules. These molecules have been in the public domain for decades. So the incentives to be the first guy to patent are very strong. So given this assumption that trade secrets are not strong, we can make two predictions. The first is that if there are a secret substitute, we should expect a peak patenting immediately after the protocol. And the second prediction would be that we should observe an incumbent advantage, that firms with prior patenting history on CFC substitutes should have a higher peak. And I don't observe any evidence for these two effects. So these two predictions don't materialize in the data. Here is month by month, 2 years after, 2 years or so after the protocol, the Montreal Protocol being successfully negotiated. So each point is month by month. So you see there are no immediate peak patenting. On the opposite, it looks like it's a sort of regular, steady ramping up of patenting activity. When I try to compare this patenting signal, but for firms that have prior experience on CFC substitutes and firms that are completely new to CFC substitute, I also don't find great differences. So it feels the incumbent advantage is not there. It seems like the incumbent advantage is building over time. The blue, darker blue line, or is the patenting, the number of patents over time mentioning CFC substitutes for the firms which before 87 had at least one patent mentioning CFC substitutes. So we see these two firms don't seem particularly different in the 1.5 years or 2 years that follow the protocol.
Eugenie, this is not strictly a clarification question, but it's really pertinent to this graph. So I wanted to ask it while you have the graph on. I mean, the narrative you are trying to say here is that maybe what happened in September 87 is that they started doing a lot of R&D in this area, and then a couple of years later we see the patents starting picking up because that R&D effort is paying off. But that suggests that maybe you could complement this evidence by going to, say, CompuStat data or some data like that and get the numbers on R&D spending by these firms and try to show us that the R&D does indeed pick up just after that. I mean, it's not 100% sure because it could be that they're just they will be just reallocating R&D from one thing to another. But I think most models would tell you that aggregate R&D should also go up.
Yeah, I mean, I would love to do that. I've thought of doing this. I've run into a bit of a, I think, a data limitation here because these firms, if you think of DuPont or Allied, they are these big multinationals that are doing a lot of different things. And to be able to implement this idea, I would need to have a breakdown of R&D spending on particular business units. And so to give you an idea of how important CFC is as a business unit for DuPont in the 80s, this is around 2%. And yeah, it would be difficult. I mean, I wouldn't be able to say that the R&D, any change in R&D spending over these years can be attributed to this particular business unit. So that is the challenge, and I'm not sure how to go around this. But again, if there are ideas, and I'm happy to keep talking about that if there may be ways of getting around this problem. Just as to finish on this firm level dynamics that I'm trying to establish here, I also find that there are many new entrants. What I call a new entrant here is a firm that I have never seen patenting on CFC substitute before that now patents. So the x-axis, the y-axis is the number of new assignees, and we see that there's a clear increase after 87. So it seems like there are new players entering this activity, this area. All right, so just to finish on this alternative hypothesis of secret substitute, I want to highlight that some other people, Grundmann, who's a sociologist of science, went as far as saying that this was possibly the most pervasive and widespread myth surrounding the Montreal Protocol. I think it's interesting to put in the context some of the statements that firms have released during this year, which I think these statements were misinterpreted, and maybe the reasons why people concluded that firms had secret substitute. But really what firms said is that they had some idea, some expectation about what promising substitute would cost. Definitely more expensive, and for that reason they were not about to do it on their own. They really needed an environmental a policy constraint to do that. They also estimated time to market up to 5 to 10 years. But again, an estimated time to market doesn't mean that the stuff is ready to be launched. It means like to get to that timeline, you need to actually do a lot of experimentation. You have some ideas, but the hard R&D work still needs to be done in practice. So let me sort of quickly summarize what I hope I demonstrate is that it's very likely that the Montreal Protocol did trigger an increase in research and innovation on CFC substitutes, and that would be the first quantitative evidence. Interestingly, we see that the magnitude is also pretty considerable. Some people had dubbed that actually as a burst of industrial creativity with a hint of irony. I find evidence that the narrative of CFC substitute being available is inconsistent with patenting trend. Now, we may be wondering how this all fits with the theory of international environmental agreements and whether we can learn any new lesson from this for other collective action problems. So as a quick, really, rough summary of what the theory of international environmental agreements is, and I'm not doing it justice really, the way that that theory is modeling the formation of agreements is by thinking about the benefits, the marginal benefits of joining an agreement and the marginal cost of doing so. And typically you end up with two equilibrium. Well, that's the equilibrium where, if you're a free rider, you just equate your marginal cost of doing so with the marginal benefits that you get from abating. But if we were to solve this problem as a united one world, where we would want to be in this cooperative agreement. And depending on the size of the parameters here, the slope of this line of the marginal benefits and marginal costs, you're gonna have different gains, potential gains from cooperating in this case. And the sort of very dismal conclusion that this theory brings to us is to say that really we only get cooperation when it's not really needed, when the gains to cooperation are not really high. And the story of Montreal within that literature has been heavily commented as being a case of unilateral action almost. Like Montreal has been argued was codifying unilateral actions. So another way of visualizing what this theory says, and I'm going to use these visualizations to bring my point, my argument home, is to think about the space of along the two dimensions, how much benefits you get from abating, right? If it's a very serious environmental problem, the marginal benefits of abating are going to be high, and the marginal cost of abatement. The color here indicates to what extent the gains from cooperation are high. So in other words, the dark area is where, you know, it's kind of easy to get abatement, and we are going to cooperate, but we may actually have done the same thing without cooperation. There's no much to gain from moving from the non-cooperative to the cooperative outcome. You can think about plotting through that space the abatement path for a particular problem. So here, thinking about ozone depleting substances, at the very beginning, the first unit may be very cheap and very high in terms of benefits that it would give you. And then overall, the last unit is going to be more expensive, and also fewer benefits may be derived from that. So the argument here of the theory is to say that Montreal is somewhere in the darker area, right? It's like something that's close to unilateral, something where we didn't have a lot to gain from cooperation. The places that where really we would have gained a lot from cooperation, you could think of the targets that were agreed later on, like a full ban, which were agreed in London and renegotiated in Copenhagen. This stuff was out of reach in '87 in Montreal. So Montreal is the sort of only thing we could get. And that is a bit of the dismal point, but here bringing the innovation argument, I would argue that it's Montreal, even though may have been a low gains from cooperation equilibrium, it's still induced innovation. So I add a little bit of induced innovation in this very simple theory to make the case that with induced innovation, the cost of abatement are reduced. And that changed the landscape of where the gains from cooperation are high. With induced innovation and the abatement cost reducing, some new equilibrium, new targets are now feasible because technological change is making this target easier to implement by the industry. So eventually, this induced innovation makes reachable allocations that were not reachable in '87. So the point that I want to bring home here is this idea that even if we start with a modest agreement, that modest agreement is in fact binding. It had trade measures here that enforced that not so ambitious agreement maybe, but that binding aspect is very effective at coordinating, at giving a signal to firms that they have to get to work, that a new market has been created for these molecules, and that therefore they have incentives to invest in R&D and launch these molecules through production. Eventually, that work, this experimentation, leads to lower expected abatement costs for even more ambitious, more challenging emission reduction. And in this way, you get to more ambitious targets being negotiated later on. So it's a case of modest agreement, which may be modest, but still induced innovation, which allows for a deeper agreement being negotiated. So what can we learn from this for other environmental problems? I think the message is that cooperation problems with high marginal abatement costs may not be doomed. Ozone depletion, ozone cooperation was successful because the beginning of the marginal abatement cost curve was expected to be low, and therefore a binding treaty was could be negotiated for the beginning of this marginal abatement cost curve. That provided the right incentives for firms, and that lowered the rest of the abatement cost curve. So that is the idea that small but binding commitments may actually be the only way of inducing innovation and lowering costs. it is unlikely that, if we have very ambitious but non-binding pledges, that can, it may not be as successful to really induce innovation. And here I want to raise as a last thought, a plug for another idea developed by Nordhaus in an AR paper at 2015 about the potential of using trade in the context of climate as an enforcement mechanism. Nordhaus tries many different levels of carbon tax and trade penalties. The overall conclusion is, in fact, the system would not be very, would not resist very high trade penalties of very high social cost of carbon. So that may seem a little dismal once again, but the point here with the Montreal Protocol is like, by starting small, but starting with something that's small and binding, you can actually build to get to more ambitious commitments. Thank you very much, and looking forward for any thoughts or questions.
Thank you very much, Eugenie. So let's do an applause. So, I might do that on behalf of all of us, but I see many people clapping. Thank you. So the floor is open for discussions. So please raise your hand, or if you're the first, you can just barge in straight away by unmuting yourself. Those of you who are not in the chat, you can also post your question via the chat, and I will read them out if necessary. Yes, so the question reads, it's by Sonke Batram, and it was posed to all panelists, but it's of course meant for you. With LDA, would a different researcher identify the same topics, and thus are results exactly replicable?
Yes, thanks a lot for the question. So yes, they're replicable. There's the only parameter that comes from the experimenter here is the number of topics that you want to discover. So that's the exogenous parameter. Now, there are ways of figuring out what should be the optimal number of topics that you think your corpus has. So there are various measures that have been developed. So I also implement that. And for example, in my corpus of patents and article, I find that 20 topics and 15 topics, respectively, or the optimal number of topics.
Very good. Another question by Francesco.
So first of all, I thought that was a really, really interesting paper, very well done and very enlightening. I do have a question, maybe not just for you, but for the other panelists as well, which is bringing this back to the topic of climate change. Is your, or, and as I say, I'm interested in others as well, view that insufficient R&D in alternative to a fossil fuel is the key problem that we are facing? That, you know, the key to climate change policy is to induce innovation in this area, or are there other challenges in climate change policy, maybe something, you know, with something to do with labor markets, sectors that we are not willing to let have a lot of unemployment in, you know, nationalistic things, geopolitical things. I don't know, but you know, how much is you're inviting us to focus on incentives for induced innovation, and I'm just wondering, and you know, that may be very well be the key challenge, but I'm just asking as an outsider, is that the key challenge?
So a very I think down to earth way of answering your question is, you know, I'm not going to claim that's the only thing and the only problem, but keeping the rest of the world constant, I'm not sure what I can do about nationalistic or populism, or I mean, for sure there are many things you know, people can do, but keeping all of this thing constant, what is sure and clear to me is that if the costs of abatement goes down, that is going to be an issue that's going to be much easier to regulate domestically and also at the global level. And I do think that incentives for innovations are only partially here. They have been there for a while because countries unilaterally decided to do things about climate change. If you think about the feed-in tariffs in Germany, that has been a major, there obviously a long literature on that. And there's a great book by Greg Nemeth about how solar got cheap. And at some point, this unilateral policy kicks in and they enable the market to survive, right? They create demand. If the demand is not there, entrepreneurs will not be there, and R&D investments by the private sector is not going to be there. There's also there's also an issue of uncertainty, right? And I think what Montreal was great about is resolving any kind of uncertainty issue. It was making clear that that was the direction. Maybe it was a mini step, but that mini step was really certain. And it was the direction of where that was going was clear. And I think that is also an issue that has been ongoing with climate, is the inherent instability of domestic regulation, which hurts a lot the long-term calculus of R&D investments. That is my take, but I would be really happy to hear what other people have to say.
So just quickly, there is a literature with Bart Harstad, who wrote a paper also in JPE, where he looks on technology and commitment and the strategic complementarities, that a lot of technology might change the incentives of future policymakers in years down the line to actually do more ambitious climate policy. Antonio Spielenberger, you had a question.
Yes. No, hi. No, it was just to answer what Francesco was mentioning. I like very much the presentation. I think that the issue is that for political, economic reasons, there could not be a successful transition without technological innovation. It's a key ingredient. It's, I think that there is a wide agreement on this. Of course, there are many other problems, but technology advancement and adoption, the two things are very important, are the key ingredient. And basically, also looking back at the history of big energy transition in the past, from wood to coal, from coal to oil to natural gas, they were made possible only because of big technological breakthrough in the other sector. Now we are in the strange situation where it's a politically motivated, because we know we want it. So we cannot rely on the endogenous technological progress on the other side, on the other alternative sources of energy, green energy, but we have to favor them. So which makes it more complicated. Just to sum up, we need a technological improvement. We cannot count on endogenous unless we have some push demand and supply on this.
Thank you. I think Thomas Hickler had a question.
Yeah, I would like to also comment on this question, how important innovation is. And I mean, of course, it's a very important component, but I think in the case of climate change, it's very clear that it's not going to be sufficient. I mean, the scale of the transformations we talk about, not only in technology, but also in society, is really enormous. And I think it's also clear that we talk about sectors like transportation, energy, and so on, which are heavily regulated. So there's a lot of policy in there actually deciding how to make money with different technological solutions. Many taxes. I mean, it's not like a plain level playing field. And then I would argue it's a heavily regulated system, and policy has such an important impact that smart policies are really crucial to promote smarter technologies. And then I want to give one example why I think that innovation alone will not make it. On the one hand, renewables get cheaper and cheaper and more efficient. And we also have some innovation, concerning how to store energy and so on. On the other hand, if we use less coal, and basically this coal is the biggest problem. We have so much coal. If you use all this, we have a big problem with climate change. However, as the demand for coal goes down, the price will go down. And with coal energy, we have the technological solutions in place. It can be cheap, unless you put a price on burning coal, you will never get rid of it. I mean, US economists, know these dynamics better. But
thank you, Thomas. So next point or question by Silvana Danero.
That was a great presentation and great paper as well. I thought, I guess like Tom, I think that innovation is necessary, but it might not be sufficient. And here's the one global problem I have in mind, the population explosion that worried people back in the 40s and 50s. They did a lot of work in bringing contraceptive technologies to developing countries, but that was not enough, and it was not enough to just distribute contraceptives, lowering the price, etc., etc. There was a need to change social norms, and that's where having massive campaigns, informing the public, changing social norms in different ways, and this had to be targeted to different populations with different backgrounds, was very important. Thanks.
Okay. Maybe you have a wrap-up answer, Eugenie, or comment. Otherwise, we move on to the next speaker.
No, I mean, I guess this is more high-level comments and thoughts now. But I think we're maybe talking about different aspects of one problem here. I mean, one is phasing, like greening, making energy low carbon. That seems to me like an area where, innovation and is going to be like a major driver. Now, if you ask about like meat consumption, and so that is driving deforestation in the Amazon, then yes, I don't have a silver bullet technology for you there. And therefore, this is more maybe about cultural change than anything else. But I think it would be useful to have this conversation on more specific issues, right? At a sectoral level. I have always, my sort of takeaway thought from having worked on Montreal and thinking a lot about climate is that in the climate change context, there is too much high-level aggregate conversations that do not, I think a sectoral approach would actually help us be more specific, more concrete about what is the barrier here and what is a possible solution, or what is the adequate optimal policy for that particular sector. Because again, the electricity generator sector will need a different policy from dealing with deforestation.
Thank you very much, Eugenie. That was an extremely interesting presentation. We go on to our next speaker. This is a paper which Tony has been working on for many years with Per Krusell. I've actually seen it a number of times, and every time I see it, I learn an enormous amount. And I always think, well, how come I can't do this type of stuff? So, and I hope that you can bring in your visuals, which you usually bring in, to impress you and to enlighten you. Tony, the floor is yours.
All right, thank you very much. Kind of set me up there, so I will try to deliver on that promise. We will show a couple of movies later on once you've made it through the first part of the talk. So there's a little payoff there. Okay, so this is joint work with Per Krusell. I just want to thank the organizers for putting together this really interesting program, a sort of diverse program on climate change, and for including me yet again on this in a program like this. So the goal of this paper is to construct a global model of economy-climate interactions featuring a high degree of geographic resolution. So think about dividing the globe into 1 degree by 1 degree regions, of which there'll be roughly 19,000 in the calibrated model. And then we're going to use this model as a laboratory to quantify the distributional effects of climate change and climate policy across space. So we're going to be thinking about climate change having differential impacts across space and not only across time. For example, here's a kind of question we could answer then. Suppose one set of regions imposes a carbon tax. How does the path of global emissions respond? Which regions would gain and which would lose, and by how much? And this is part of a growing sort of newish, not even really new, it's becoming an established literature on spatial equilibrium models of climate change. I've listed a bunch of people there, including some people on the program today. But I won't spend time on that literature review today. All right, so I'm just going to plunge right into the model. this is a relatively short presentation, so I'm going to try to keep equations minimal. And I've summarized the model kind of in one page here. And this will leave time for some of the visuals at the end. So you want to think about in each region, these 19,000 small regions, there are forward-looking consumers and firms who are solving consumption savings problems like what we're used to seeing in macro, and also making an energy use decision. There'll be no migration in the paper. So that's a limitation of our framework. On the other hand, there will be movements of capital across space. So there will be economic resources sort of adapting to climate change and moving across space. We'll have neoclassical technologies for producing both final goods and energy. And the inputs are capital, labor, and energy. Labor will be, the number of hours will be fixed, but the efficiency units of labor will change over time in response to climate change. The energy sector is very, very simple here. We're not really innovating, to be honest, in some dimensions, but we are innovating in others, in particular trying to bring in heterogeneity in a relatively simple model, but still in a very rich calibration. So we just modeling coal is non-exhaustible, but so there's just, you just think of this on non-exhaustible, we're thinking of energy as coal is non-exhaustible. It's just, it can be produced using capital, labor, and energy. But we are going to allow energy to exogenously become green over time because we think that's important in a realistic calibration. So we're completely punting in this paper on any questions of innovation that were discussed in the last paper. I do think those are quite important, but that's not our focus today. Regional total factor productivity. So like in other models of climate change, other integrated assessment models, the damages from climate will come through changes in total factor productivity. And each region will have its own TFP, one component of which is exogenous and captures things like culture and institutions and property rights and so forth, the usual sorts of things. But another component will vary with the region's climate or temperature. This will be a completely deterministic model, so ignoring any of the important risk issues that were raised yesterday. And you can just think of, we'll just have one weather variable, which is temperature, and that will be the region's climate, and it's changing over time. Now, regions will be able to save in one version of the model, not only locally, but globally. So there'll be, in one version of the model, unrestricted borrowing and lending between regions. So that capital market will connect regions. And then regions will also be connected through the climate system, as I'll explain in a minute. In another version of the model, we're in autarky, so that regions are only linked via this emissions externality that we're all familiar with. And it's going to turn out that, somewhat to our surprise, that the results under these two extreme market structures for this particular calibrated model didn't really change the results very much. So the results were kind of invariant to this. So we're mainly going to focus today on the unrestricted borrowing and lending case. Now, I'll maybe have some intuition for that later. So it's important to note the model does allow for adaptation of a certain form. It allows for consumption smoothing within regions. So that's the usual kind of intertemporal substitution of consumption in response to changing productivity. As your regional climate changes, your productivity changes, and you might want to smooth your consumption over time. But when we have international markets, we'll also have capital mobility, or so-called leakage. In response to differential carbon taxation, for example, some resources might then leak elsewhere. Some capital might leak to other regions that are taxed less. Of course, I can't see the chat. So if you want to interrupt me, or if someone wants to raise a chat question, I'd be happy to answer it. All right, so that's the economic model. Now let's just talk about the climate system and the carbon cycle. These are the other two components of any integrated assessment model. And these are very simple, really just following on Golosov et al. Paper. Per Krusell was a co-author on that paper, which was a one region model of the world. This is a multi-region model of the world. And the climate system is very simple. We're just going to relate the current global temperature, T, relative to the pre-industrial period, will just depend on the current carbon stock and on the pre-industrial carbon stock according to the sort of a standard kind of setup here with a very quick response of temperature to changes in carbon. Lambda is climate sensitivity. So if S were to double relative to S bar, that would lead to a change in the global temperature of lambda degrees, and we'll set that to 3. And the carbon cycle is modeled very simply here as sort of two conceptually different stocks of carbon. One is permanent, so some carbon kind of stays around for thousands of years. Other carbon depreciates slowly into other sinks, and we have a very simple linear structure with 3 parameters that we calibrate to, how this carbon cycle works in the real world. All right, so this is a simplified climate and carbon system, but climate scientists who I've talked to don't think it's sort of nutty. It's a reasonable first step. All right, so what's important here, though, and what's new here, is this idea that each region has its own temperature, separate from the global temperature, and each region then, when it's figuring out how to make its consumption savings decisions and energy use decisions, needs to know how its own temperature will vary over time. Now, there are Earth system models that predict these sorts of things. There are these complex global and regional climate models, but it's not really feasible, although I'm working on it, to combine these with this economic model. So instead, we're going to use an approach called pattern scaling or statistical downscaling, where the local variables are just function of a global variable, the global temperature. So the idea is that each region will have a sensitivity coefficient to changes in global temperature. Your sensitivity coefficient might be 2, meaning that if the globe warms by 1 degree, then you'll warm by 2 or 3 degrees. Or it might be less than 1, meaning that you warm by less than the global temperature. And we computed these coefficients by working with climate scientists who ran these complex climate models into the future, so out of the historical data, and gave us estimates of these sensitivities by running sort of an ensemble of these types of models. So I think my next picture is in fact these sensitivity coefficients. And now you can see like the resolution we're working at. So there are 19,000 little cells there. You can kind of make them out a little bit. The coefficients range from 0.4 to 5.2. So for example, it's well known that northern latitudes will warm faster than other latitudes. And in fact, you can see this. Parts of northern Russia might warm 3 or 4 times as quickly as the rest of the globe, whereas other parts of the globe will not warm as quickly. All right, so the weighted average of these coefficients across the whole world, including the ocean, would of course be 1 by definition, because the global temperature weighted average of the regional temperatures weighted by area. All right, so I'm going to move along here. All right, so and now we're going to get to more of the calibration issues, but already you've got a sense for kind of the scale we're working on. All right, so just to be clear, so the equilibrium conditions are that, so you can make this kind of simple now because of the downscaling model that relates a local variable to a global variable. All each region needs to know is just what's happening to global temperature. This is what makes this feasible. So consumers and entrepreneurs in the model with unrestricted capital markets will take the global interest rate path and the global temperature is given, and then make optimal energy use and savings decisions. And then the implied path of global emissions, so adding up all of their energy use decisions, has to generate the path for global temperature as given by the climate system and the carbon cycle. And the global bond market has to clear it every period. Now, with free capital mobility, it turns out that this model aggregates. So you only need to solve the problem of a global standing consumer, which really simplifies its computation. And in fact, this is a sense in which at the aggregate level, and it's by design, you're going to see that this model just looks like the DICE model or the Golosov-Haddad model or any other one region model. It's going to be rigged up to look that way, but it's going to have all these distributional implications that are fleshed out that you don't see in one region models. So now in autarky instead, the model doesn't aggregate. So there you need to solve like literally 19,000 different dynamic programs, one for each region, because each region has a different path for its future productivity, as we'll see. But that's not really that hard to do, partly because you can put this on a parallel computer and solve these simultaneously. So, all right. Okay, now we're going to focus mainly on the free capital mobility case, but we needed to solve the other one just to kind of check that it didn't make much difference to the results. So we have done that, but I'll focus mainly on the case with unrestricted borrowing and lending. All right, so now let's talk more about the regional, let's talk about the regional data. So again, the unit of analysis is a 1 degree by 1 degree cell containing land. There are about 19,000 regions. We actually subdivide regions where they're country borders. So we maintain country identities for use later, as you'll see in some pictures. So there are 19,000 of these regions. We have some temperature data from Matsura and Wilmot, and we're going to calibrate the sort of the base year GDP across regions to 1990 data from Nordhaus's GECON database. So here is looking at average temperature, average annual temperature over the first 20 years of the what century is that? The 20th century. And it ranges, this is in centigrade. So you have some very, very cold places from minus 64.7 up to 30.8 average temperature centigrade. All right. And we're going to see that map evolve over time in response to climate change. All right. Now let's see. Now we're going to look at just to give you a sense. Here's log of GDP. So it's GDP in each region as constructed by Nordhaus's database. So there you go. That's what GDP looks like, and that's going to evolve over time too. Okay, in response to climate change, we're going to make predictions for all this. All right, so the calibration, some of it is kind of boring and sort of standard, in other words. So we'll have an annual time step, log utility, a discount factor of 0.985 because of an interest rate of like 3% or something once you factor in the growth rate. The production function, it will be really in the end Cobb-Douglas, but in principle, we're allowing it to be CES in a ball of capital of labor and energy. And I've highlighted here, let me see if I can just highlight this part right here. This part here is efficiency units of labor. All right, so each region has some capital and some efficiency units, which are given by a product of AI, which is the sort of exogenous part, or part that doesn't depend on temperature, reflecting institutions and human capital and any other kind of factors that lead to the wide dispersion in GDP that we see around the world. But there'll be this other component, D, which is a function of the local temperature. And we'll spend a bit of time discussing how we calibrate D. So the parameters of technology are fairly straightforward. And what we're going to do for the base year is we're going to calibrate initial region-specific capital and the product of these two. We can't identify those separately from the data. They show up as a product. So we're going to choose that product to match the regional GDP, as I said, in 1990. And we'll assume that initially marginal products of capital is equalized across regions. All right. So then we'll choose the price of the unit of energy in terms of consumption and the share parameter theta and the production technology to give us the right total emissions in 1990 and to give us an energy share of 6% along the balanced growth path. And energy use, as I said before, slowly becomes green. And let me just show you what that, and we just made this up, to be honest. So this is what it looks like. So in 1990, carbon emissions, none of them are abated. Imagine there's some kind of carbon capture technology that slowly comes into use, if you want. That's a fine metaphor here. This is a proxy for the backstop technology that Nordhaus puts in a lot of his models, for example. And then slowly over time, more and more of emissions just become green, and it's exogenous. So eventually all emissions are green, or they're captured somehow and not emitted into the atmosphere. So now I want to get to the kind of interesting part of the calibration, which is the regional damage function. So we have local temperature. We know how it evolves relative to the global temperature. But how are we going to model damages in region I from global warming? Well, we're going to use a reverse engineered kind of approach. So we're going to imagine that there's a U-shape, an inverse U-shape of local temperature that's common across all regions. All right. And this U-shape will be normalized to have a maximum of 1 and a minimum of 0. And so what it captures, it doesn't capture sort of permanent productivity differences captured by the A that I showed earlier. Instead, it captures variations relative to that component. So you may be operating at what is the optimal temperature, and I'll show you that picture in a minute. And as you warm, you move away from the optimal temperature, and relative to the sort of permanent component of your productivity is going to decline. Or you may be originally in a cold place, and so your productivity the component of productivity coming from temperature is low relative to the maximum, and eventually you'll catch up as you warm to that maximum. And so how are we going to calibrate the D? We're going to go backwards, and rather than sort of add up damages by sector and do what Saul Sang was doing, for example, which I applaud actually, but we're taking like a different approach here, which will calibrate this function so that the aggregate damages from changes in the global temperature match Nordhaus's Dice damage function. So it's getting back to this point that this model, and the last point, I guess, kind of a key one here, is that this model at the global level, this high resolution model just replicates the findings of standard one region economy climate models. It's rigged to do that. It gives the same aggregate damages. There's nothing really new there. I view that as kind of a strength, because now we can we understand what's going at the global level, that adding things up. Now let's look at the regional level. So here is what the function ends up looking like. All right. So just to make sure we understand this U shape.
Tony, can
yes.
I just interrupt for 1 second? There is a question by Matt Kahn. I don't know, Matt, can you unmute yourself, or shall I ask the question for you? Okay, Matt asked a little bit a question about this is paper by Deschênes, Baraka, Clay, Greenstone, Shapiro on adapting to climate change. And the question is, can there be induced adaptation investments, such as, for example, the stand-in air conditioning? Is that any part of your model, or what do you think of that? So there's not much adaptation apart from the consumption smoothing going on, perhaps.
Yeah, that's right. There's no other adaptation formally in the model. My understanding from Nordhaus's damage function that it includes adaptation in the way it's constructed. So it is built in sort of adaptive responses and sort of figuring out what the aggregate damages from climate change might be. And to the extent that we're choosing our local damage function to replicate those damages, we're kind of building in adaptation kind of indirectly that way, or kind of in the background. But certainly it's not formally in the model. And I do think, I've said this a number of times, I think it's actually useful to explicitly model adaptation.
So Matt mentioned, for example, things like Neil Good's, think of Paul Romer type models, and so that may be a form of adaptation.
Yeah, I think that's not going on here. It's sort of implicit in the calibration to the extent that Nordhaus's Dice damage function has factored in adaptation in the way he calculates his aggregate damage function, but it's not explicitly captured here. Okay. And I do think it's important. I think another panelist has maybe been working on that. So again, often when I give this talk, I'm always apologizing for all the things we've left out, but I think it's a strength in a way, because we're going to focus on this heterogeneity component, and we'll kind of leave out other things that may interact with that, and then we can put those in later and see how they interact. All right. All right. So this is the damage function, where really it's capturing regional TFP. So, relative to your permanent TFP. So it turns out that the calibrated value is the calibrated optimal temperature is about 12 degrees Celsius. And that would give you a value of 1. And as you move away from that, your productivity falls off. So if your region warms from 12 to say 14 degrees, you would fall from 1 to 0.95. And you're able to kind of read off, from this graph. Now I'll explain a little more in a minute how we did this. But let me just describe it in words. I have a whole page of equations on it as a new way of trying to explain it, but we'll see whether I want to actually do that. It's the next slide. but let me just say it in words. So what you want to imagine is, we start off in 1990 with regions located along the x-axis in different places. Some are at -10, some are at 0, some are at 12, some are at 20. I just showed you a picture of average temperature. And as they warm, as the globe warms, they're all going to move to the right along this graph, along the x-axis. Some will move by more than others because their sensitivity coefficients, their sensitivity of temperature, local temperature to global temperature can be larger or smaller. Some will warm by more, some by less, and they'll make optimal consumption savings decisions. And so their GDP will also change. And so we can add up the total change in GDP caused by the global warming. And that's a measure then of the damages caused by global warming. And we would like those damages to add up to what Nordhaus would find in his damage function. So for example, we might do an experiment where we go forward by where we warm the globe by 1 degree, everyone shifts to the right on this graph, they make optimal decisions, their GDP changes, we add up the damages at 1 degree and see what they are. Then maybe we might increase the temperature by 2 degrees and add up the damages. Maybe 5 degrees, add up the damages, and then we want to match the aggregate damages, say at those 3 points. Well, we're going to choose 3 parameters in this U shape to match those aggregate damages at those 3 points. So the 3 parameters are the peak, that's a choice variable, plus 2 curvature parameters that govern how quickly this bell shape falls off asymmetrically, slightly asymmetric, either to the right or the left. All right, so that's in words what we're doing. We're picking these 3 parameters so that when we add up global damages from climate change using this model, it exactly matches, won't give you any surprises, exactly what you're used to seeing from one region economy climate models. And there are all the equations. And it's, I quite like that slide because it's a simple way of explaining what we're doing, but I can see it's hugely busy. And so I don't think we're going to do it right now. I could come back to it. Let me get to some of the results and I could come back to this. And I could pause. This is like a simplification of how we actually do it, but it kind of captures in one page sort of how these parameters phi, you can see there's some parameters phi here in the damage function, how they're chosen. All right, I could pause for a second because I think what I'm going to go on to next is actually showing all the results. All right. I think I moved quickly, kind of on purpose, because I want to make sure I get to the results in the short amount of time we have.
Tony, can I ask a quick clarification on?
Yes, please.
So there is no policy, right, in the model so far?
Oh, right. So there is going to be policy. What we're going to, I didn't describe that. Yes, when there is policy, we'll have carbon taxes imposed locally and then rebated and their proceeds rebated lump sum back to the local regions. Policy can vary by region. And what we're going to do, we're actually going to impose like an optimal carbon tax, but it will be an optimal carbon tax for the global stand-in consumer, kind of ignoring distributional issues. Because remember, the model aggregates under free capital mobility, so we can solve that optimal carbon path, and then it's just exactly what you'd find from Nordhaus or Gauss et al. So the policy will be in here. It'll be part of what I talk about for sure. Does that make sense? Okay, thanks for the question. Yeah, I omitted it from the description because, just to keep it simple, but we'll have policy in that way. There'll be no transfers across regions. Larry Kotlikoff's paper yesterday talked about transferring across generations, and you can make transfers across, across regions that might be beneficial for, make the whole world better off. But we're not doing that. We're imagining that each region has a local government. All right. So this is showing the calibrated U shape multiplied by 100. All right. So in other words, going back to the U shape, some countries or regions are near 11.6. That's their average temperature, so they get a 1 or 100. Some regions are at 20 degrees, so they get maybe a 75 or an 80. Some are colder, and they also get lower values. So now here are all the values. And so the hot values, the red values, are sort of high productivity places in terms of the productivity effects of temperature. Remember that there's this permanent component that is unrelated to temperature. All right. However, this does sort of come out the way you might expect, but notice that we didn't kind of rig this in any way to do this. We literally just tried to use the model to match aggregate damages from standard models under the assumption that there's this common U shape. So you can see like a dark red band going across the parts of the US and through Europe over to China and Japan and some in the South. You can see blue in the Sahara, that's low productivity places, low productivity coming from warm temperatures or very cold temperatures up north in Russia. All right, so it sort of comes out the way you'd expect. In fact, most GDP, as it turns out, is in the model, once in this calibration, most of GDP is produced in regions that are close to the peak of that U shape. It'd be a little bit, the calibration sort of would seem a little bit odd if that weren't the case, I guess. But there was no sense in which we rigged it that way. All right, so let me show you results. So I'm moving right along here. First, we'll do laissez-faire, and then we'll do this policy experiment. We'll actually impose a common path for carbon taxes for all regions. We've done some other experiments where say only some regions or some countries impose. I won't present those today because it's not time. And we're mainly going to focus on relative effects, not aggregates, because as I said before, you've seen these aggregate paths before. Nonetheless, I will, and I'll get the main findings. So then, then we're done in a sense, but I hadn't even shown the pictures yet. So Rick's not happy. I was supposed to be fun, I guess. I don't know if I've been much fun yet, but we'll show the movies in a second. All right, so the main findings are that climate change affects regions very differently. The stakes are big at a regional level. So some regions gain a lot, some lose a lot, even though the model makes the same aggregate predictions as, say, the DICE model. Though an optimal tax on carbon would affect welfare positively in some average sense, just like in the standard one region model, there's a large disparity of views. Many regions gain, many lose. The findings I said as before are close for the two extreme market structures. And then a more recent result, I looked at inequality and how that changed. And you can see that climate change leads to large increases in global inequality, both across regions and countries, and that the tax on carbon mitigates these increases only to a small degree. All right.
Tony, sorry, can I interrupt? Can you clarify what you mean by optimal tax on carbon here?
Yeah, so it's the optimal tax, right? So let me say it again. It's the optimal tax. So let me go back. I mentioned that there's the model aggregated back here in point 2. The model aggregates. So I am going to pretend like the social planner cares only about sort of the welfare of this global fictitious stand-in consumer, and is going to pick an optimal carbon path, assuming that those are the preferences. All right. So in other words, inequality is going to play no role. So it's okay. And one can imagine other, and people have worked on that too, other global, optimal carbon taxes that might give a role for inequality, say, but we're not doing that today. So basically, at the aggregate level, it just looks like the DICE model or say Golosov model at all. And I will just compute that optimal carbon tax path in that model.
I mean, I have to say, I mean, given all the trouble you've gone into creating the disaggregation here, I find it very odd that then you use that kind of social welfare function. I mean, it would seem much more natural to have someone who add the utilities of all the regions.
Yeah, I agree with that. And I think, we want to do that first to kind of see, kind of what happens. And we're going to find that there are, big effects in inequality and that people really disagree. And so then it would cry out for a more thorough welfare analysis that factors in that heterogeneity. I agree with that point. That's something that one could do following up on this. All right. So, so I will show just 2 graphs of aggregates. So this is global emissions, first under laissez-faire, and then under this optimal carbon tax, though, as clarified exactly what I mean by that. So this, so there you go. The carbon tax reduces emissions. Eventually, emissions fall off because the green energy kicks in exogenously. Eventually, the emissions are zero. And this is showing the global temperature. It increases for a while and then falls down again because there are no more emissions. And nonetheless, and so some of the carbon dissipates into other sinks, but some of it lasts for a long time. So in some sense, that's why, there's a big problem. It's essentially a permanent problem on the scale of thousands of years. It's this permanent component of carbon in the atmosphere. And the temperature goes up by less under this tax path that we use. All right, but now let's get to the regional results, which is more interesting. So I'm just going to show this picture here. So we have a movie that's going to show the change in regional temperature under laissez-faire. And I'm just going to have to pause it, make it really big. Hopefully, there we go. So we're going to start out in the year 1991, when every region is at its baseline temperature in 1990, basically. So dark blue means your temperature hasn't changed yet. And now we're running the model forward, okay? We built this whole model and everything's running forward, and we're going to observe how the change in your temperature, okay? And you'll see that some regions gain as much as 16 degrees, some by as little as 0.3 degrees along the way. So let's go. All right, so I'll just run this. I'll do it twice. So maybe I'll pause it, certain points. Going year by year. So now you can see we're in 2061, and you can see the patterns are changing, the colors are changing. And you can see that in northern Russia, especially, which is very sensitive to climate change, you can see the change in temperature getting larger faster. And then we'll keep running this out. And now you can see it, there you go. That's the change in temperature. And it basically just matches those coefficients that we had before times, the global temperature change, which is eventually 4 degrees here. So you multiply by your coefficient to get, how much you warm. So sometimes I like to run these again, just so you can see it again. So, I do enjoy these pictures, but I think not just because the colors are fun, but I think it's almost like it's too much data to absorb, like by looking at a graph. You need to kind of see it visually to see what's going on. So this is when I really understood what was happening in the model. All right, that's just the physical side of things. Now what do I do to get out of this? All right, so now I want to, okay, so now let's look at.
Is there a reason just why the UK seems to be spared global warming in your picture?
Well, we'd have to go back to the sensitivity coefficients, which apparently, maybe I won't go back now, but they just happen to not be very large. And those coming from the climate science. Now I'm going to show the regional TFP. So remember, we'll just have to pause this, make it big, restart it back to 0. Okay, so here we are. This is the picture you've already seen. I showed this to you before. Because it's essentially 1990. And then you're going to see, what I want you to watch, I guess, is this dark red band going across sort of the northern latitudes, mid-northern latitudes. Watch it move north as the globe warms. The optimal place to operate is going to move north as well. So let's watch this go up. So you can see that now we're, maybe 2082. You can see that Montreal is now the optimal place to operate, not New York, or maybe Stockholm becomes more attractive and not Paris. All right, so that's just people that's regions moving along the U shape. All right, let me do it one more time. Look at it, and then what I'm going to do next is I'm going to show change in regional GDP relative to some trend path. And in the background, there's a 1% growth trend going on here that's common across regions, something else we also could calibrate in a better way. All right, so let me cut this out.
Tony, can I just ask you a question?
Yes.
About that picture, I don't want to make you run it again, but the kind of Central Africa, Equatorial Africa there was no worsening there in TFP, if I read the picture.
Yeah, that's right. Yeah, because they are hot regions. Let's watch Saharan Africa, say. sorry, there was worsening. There was worsening. So are you talking about, say, the dark blue in Africa there?
Yeah, it always looked the same dark blue to me.
Yeah, but it's just the scale. So if you watch it more closely, I will watch it more closely too. It's kind of light blue now. So watch like, I don't know, whatever countries those are there, Mali or something. Watch that. You can see it gets darker blue, right?
Yeah, okay, sorry. I
Yeah,
probably,
it's no problem. Yeah, and it's partly, a question of scale. What's the right color scale to use? So now let's look at regional GDP, and then I'll talk about, so it's the last picture I'll show that just shows and then I'll show some static pictures of changes in policy. So here we're showing percentage change in GDP relative to your trend path. So you're going to be warming. That may make you more productive or less productive. It will move you off the trend path you would have been on if there had been no climate change. So that's what we're looking at, sort of how far off you are from that trend path. And some regions are going to gain a lot and some lose a lot in terms of GDP. And you can see that northern Russia becomes more productive, so they build up more capital. Either capital flows there, or in autarky, they recognize they're more productive and just accumulate more capital, that sort of replicating the allocation you would get if it could flow freely. And you can see that Africa gets poorer because it gets hotter and less productive, so it accumulates less capital, has less output, and people are worse off there. All right, so this is kind of not a surprising picture, I guess. Regions that were cold and get warm are happy. Regions that were warm and get hotter are not happy, to put it bluntly. And you can, capture exactly, these outcomes. Okay. So I realize that we're maybe getting a little short on time here, so I will stop that picture. And now I will talk about winners and losers from tax. Okay, so this is the case, again, with free capital movement. The picture with autarky, looks a little bit different, but it's basically the same picture. That's sort of the idea, that doesn't make a whole lot of difference. So so what's the scale here? So it's asking if everyone has this common global tax on carbon, it's asking how much worse off you are in consumption terms. So the scale on the right side is percentage change in annual consumption. So for example, sub-Saharan Africa gains a great deal from a carbon tax because they're hot and don't want to get hotter, and they want to slow that down. So they might gain as much as 4% in annual consumption, which is a very large number, relative to the average gain for the globe with the standard consumer, which is less than a percentage point.
Sorry, Tony, can I ask you a clarification on that? You just said, so Africa gains about 4% compared to no tax.
Compared to no tax.
But how much were they losing so that's an interesting metric. The other metric is how much does it make the situation less bad compared to the
I don't have that metric, right? I could compute like how much worse off they were. Right, I should compute that. Yeah, great. These are great suggestions. I mean, with all these things we could answer, we might as well. I don't have the answer to that. My guess is that it doesn't help a whole lot. Because I don't think the carbon tax is that effective at keeping the global temperature from rising a fair amount, apparently. So,
yeah, that's why I asked the question, because when you show the picture of how much the carbon tax reduces the warming, it was very underwhelming. It was like,
that's right. It's very underwhelming, and I suspect that the number you're asking for would be underwhelming as well. Yeah, but it's something we should compute. It'd be a nice thing to compute, actually. So by contrast, Russia, and I even at one point had a quote from Putin, is saying that we would welcome climate change so we could, have a better grain harvest. So sure enough, Russia doesn't like a it doesn't like a carbon tax because they would like to warm, and they're prevented from warming by a carbon tax, and so they're worse off. All right, I will skip this picture here. I'll go to this one since we're running short on time. That previous slide was just putting some numbers that capture what's going on in that big picture I just showed. So here I've done it by countries instead. So I've treated every country as having like a stand-in consumer. And you can see that the US as a whole, there's heterogeneity across the US, but as a whole, maybe the US gains maybe 0.8% or 0.5% consumption per year. Countries in Southern Africa lose a large amount. It's just, I think it's useful to see it by countries as well, that even though there's heterogeneity within countries, there's heterogeneity across countries. Another useful picture is to imagine people voting. So in the US, there are about 900 regions. They're all identical with agents within the regions. Regions feel differently. Some like some like climate change, some don't. So some are in favor of a carbon tax, some aren't. So you could ask the regions if they each get one vote to vote. Many have even done it by population weighted. And then you can see that 77% of the US would be in favor of a carbon tax. All of Africa is in favor of a carbon tax. Russia may be only 20% in favor of a carbon tax because they're affected differently. So I think these graphs are very useful because they also show that one impediment to climate change negotiations might not just be the free riding problem, but also that effects differ around the globe, and so we don't agree on the effects, and so maybe we need to arrange transfer payments and so forth so that we can all be made better off. Finally, I'll just show something about inequality. I'm almost done here. I think 2 more slides. So this is showing regional, I guess I'd rather let's just go to countries for now. So this is showing per capita GDP by country in the model with and without the tax. And again, the tax is underwhelming here, going back to your point. So this is the 90-10 ratio of GDP per capita. It was 32 in 1990. And at the peak of climate change, it'd be something like 46. So there's a big change in inequality, only partly mitigated by carbon tax. So let me stop here. So the main result is that climate change is about relative effects much more than about average effects, at least according to our model. There are largest agreement about taxes. So one can imagine a role for large transfer payments, and it'd be fun to calculate those. It's something else. I think Larry, when I presented this in BU, suggested calculating that. We should do that. The market structure doesn't seem to matter much here. Yeah, let me just, I'll finish let me just finish. Go ahead. Well,
yeah. Which way are these transfer payments going? Because normally people think that transfer payments should go from the rich countries to the poor countries, say to Africa. Well, but your results suggest the other way around. Almost.
Well, I think that the pie is getting larger here, and with free capital mobility, sort of with complete markets, essentially, we should be able to then arrange a transfer so that under the carbon tax, everybody's better off. I just think that must be a theorem. It wouldn't be true in autarky necessarily, but I think it will be true with complete markets. So we could arrange these. It's not designed to address global inequality. It's just designed to get us all to sign on to a uniform carbon tax path.
But normally people say you have to pay transfers, say, to very poor countries because they've got other things on their mind than climate change. They just want to come to the end of the day.
Well, here that would happen too, I guess, because it turns out that many of the regions that are hot are poorer countries, as it turns out. So just because of that reason, it would turn out that many of the transfers would probably go to sub-Saharan, would go to Saharan Africa or Africa, just for the reason they all, no, I guess I maybe had that backwards though even. No, I guess I had that backwards now. You made me think. It might have to go the other way, that because the African countries are gaining so much, they'd have to compensate, say, Russia.
So this is very odd, isn't it?
That's very odd.
So if you go to Paris, you'll be chucked out of the room.
Yeah, that's very odd. In the sense that it's not what we normally would think. I guess we normally would think that, and maybe it goes back to the question on adaptation, that some parts of the world are better able to withstand the difficulties of climate change than others, are more adaptable. And I don't really have that in the model. So for that reason, you might want to give resources to countries that are somehow less adaptable. There's also a sense in which we're trying, it's like, it's a reparations argument too sometimes, that it was the rich countries that kind of caused this problem. Now, and so they should maybe be transferring some resources to countries that didn't contribute to global carbon emissions. Even if the carbon tax would even if they don't even apart from carbon tax questions. So let me just say a last step here is that we would like to merge this simple model, actually, because it is relatively simple, with the Norwegian Earth system model or some Earth system model. I'm actually working on this with 2 climate scientists from Norway. And the one reason for doing this is that at the regional level, you'd like to bring in sort of big random events, like extreme type events, so extreme temperatures or floods or changes in wind patterns that might cause damage. And I think it is feasible actually to merge this model with an actual Earth system model. So you get away from having to simplify the carbon system, which would be great in the climate system, but you also get access to all these really interesting weather variables that can then make damage functions more interesting. And maybe get at what the real question too is that it's not just, there's heterogeneity in the types of damages across different regions. Okay, I'll stop there. Thank you very much for your attention.
Thank you very much, Tony. It was an absolutely wonderful presentation. I will open the floor to questions. There is one question in the chat. I'm not sure whether Nico Jaakkola, can you unmute yourself? Or
yes. I think I can.
Yeah, off you go.
Yeah. So this is more or less related to what Rick was saying, essentially, that these transfers seem very odd. I mean, your model is saying that it should be the Northern European countries who would be against climate policy, and places like the US and Africa who would be for. And it seems that that's almost like the polar opposite of the climate politics that we observe. So should we infer that climate politics are not based on expected damages and sort of minimizing those, or what do you think?
Yeah, it's a provocative question. I was suggesting that that this can inform political discussions. On the other hand, if it goes the opposite way, I mean, yeah, I don't know. I mean, it'd be interesting to maybe find a graph. There must be data on support for carbon policies by country, surely, and to compare that to this graph. I don't have much more to say there. It makes you think a bunch of things. Maybe I won't speculate right now, but it's an interesting question.
Yeah,
I mean, Francesco Caselli.
I mean, it might actually agree with Russia though. So like Putin has this quote that we welcome climate change. I used to put it in the presentation. So for Russia, maybe it does. It is consistent. Maybe. Yeah. Go ahead.
Thanks.
So can I say? I mean, I think picking up on the question from Nico and the answer, I think Tony. My sense is that the problem is that you're missing some very, very, very crucial aspects of the cost of climate change as perceived by people, which go beyond the ones you model. I mean, once you mentioned, which is the weather aspect, which I think might change the picture of who's in favor and who's against. But I think there are other big things. Some of them Thomas talked about yesterday, actually. One is biodiversity. Which is something that everybody is invested in. But the one that I wanted to stress, particularly because of the nature of the model you wrote, is migration. I mean, once you explain to Putin that with the temperature changes that you model, you're going to have the entire Asian subcontinent and the entire African continent and try to migrate to Siberia, I bet you that Putin will change his mind about whether Russia welcomes climate change. And I think that's critical. I mean, I think when we look at climate change, we need one of the very first in the distribution effect, one of the first order of businesses is that unless you triple the spending on your fleet and you put the fleet to systematically shoot cannons at the literally billions of people who will try to move to the north in a consequence of the changes in temperature you predict, I don't think you're going to find a single rational person who is against very heavy carbon taxes.
Okay, so
I think that's a limitation of the model. There's some work by Rossi Hansberg and co-authors. It's a very different kind of model with a lot of things going on, but that does allow migration. Certainly with this model, you can sort of calculate the additional pressures to migrate beyond already the global inequality that we have. The additional pressures to migrate, you could kind of quantify that coming from climate change. And yeah, I agree, there are large incentives. So we would like to include that at some point. It's a little bit harder thing to include actually, because migration, once you include migration, you have to kind of imagine fixed cost to migrating, and then you have to think about how to solve that model. So it's a little trickier, but certainly a very valid question.